Okay, this is Chapter 2, Section 6. We're just going to look at some graphs of basic functions and introduce some concepts, especially for those who are going on to calculus, that will be important, and indeed they're really important in all of mathematics, especially analysis. So this is an informal definition. Those in calculus will actually see the formal definition later on, and it will melt your mind. I remember when I first heard it, but then you hear it a few times and you get used to it and you can figure it out because there's an easy visual way to see the formal definition. But for right now, all we're going to do is look at an informal definition, and this is really informal. So we're going to look at the graph of a function. So a function is continuous over an interval of its domain. So the domain interval is always our x-axis here. If its hand-drawn graph over that interval can be completed without lifting the pencil from the paper. So if we look at this graph here, and I try to actually trace over it, I'll make it actually bigger so you can see where I'm tracing. I can trace over, not very good of course, but I can trace over all of this graph, and I never have to lift my pen off the paper. So that means over this interval here where I traced, so from right there to right there, so this interval here, and usually we deal with open intervals, so that's about it's about minus 2.5 to 2.5. We know that this function, whose graph we have, is continuous. Now all we have is the graph of this function. We don't have the rule of the function, so we can't really say much more about this one. On the other hand, over here, if you notice, I can't actually do that with this line. This hole right here, which I'm exaggerating, means there's a point there with no part of the graph. So in order to graph it, I have to lift my paper off the line. So this is not continuous. Over, and we're going to do open intervals here. That's 1, minus 1, minus 2, minus 3, over minus 3, minus 1, minus 2, to 4. But it is continuous. But it is continuous. This is the important part. Over, say, minus 3 to 3. Because right here is minus 3. This is the domain, and clearly right here is 3. So from minus 3 to 3, not including 3 itself, I can draw the graph without lifting my pen off the paper. So the point is, we don't talk about entire, we have intervals of continuity. Now, if a graph is continuous over its entire domain, we say that the function is continuous over its domain. And many times we care about certain points where it's discontinuous. And that's about as far as we go into that concept for right now, but it's kind of good to plant the seed of continuity. It is so absolutely important. So the goal of this particular class is to look at some graphs of some major functions. Because what we're going to be doing is we're going to be creating new graphs of functions from the basic ones by rotating them, by reflecting them, by making them wider or making them more narrow. And you can start with the basic graph and then apply transformation rules, and it gives you a new graph. And transformation rules of graphs are really important. If you think about any Pixar movie or even a video game, their motion is pretty much determined by transformational rules, where you have an object here and you want to move it over here, or you want to change or deform its shape. All of those are really interesting, and of course, complex transformational rules. So the first of all functions we have, and it's so simple, is called the identity function. It means your input is the same as, let me restate that, your output, which is this right here, is exactly the same as your input. It's the identity function. So again, if we have a function, the first thing to remember, it's defined over a certain domain. And that's always in the background. What is its domain? And its domain has to do with the input variable. The output, so that's the input value, and it's x. And that input value always comes from the domain. And for our class, the domain is going to be some subset of the real numbers. And graphically, the domain refers to those numbers taken from the x-coordinate. So this is the output here. Now this is just a value, but of course it could be some really, C is some rule, or actually the result of some rule applied to the input value. And it's important to know for this, for C, C belongs to the range of f. Now remember, we're calling our function f here, but functions can be g of x, h of x, etc. The variable one chooses doesn't have anything really to do other than if you have a lot of functions, you can go and see what g of x is, you can go and see what h of x is, etc. So the identity function is literally a function that leaves the input variable unchanged. So it passes through the function machine, if you want to think of it that way, unchanged. So f of x is equal to x. Well, let's do a little bit of thinking here. What would its graph look like? That's the same as y is equal to x. Remember, f of x is the same as y. So what is a point going to look like on that graph? Well, here is x, y, which is the same as, that's a point. We're pretending all of these points I'm writing down are points on the graph of f of x. So that's x, f of x. But f of x, I'm looking at this one right here, is just equal to x. So let's look at a few points there. It's going to look like this. If x is any value in the domain, its output will be the same. It's a really simple function. Now if you actually go to plot this, you will quickly discover something. So let's plot that. So over here, my input value is going to be 1. So this is my x-axis. So my x value is going to be 1, and my output value is going to be 1 also. So that corresponds to that point right here. If my input value is, well, I can do 4. If my input value is 4, my output value is 4. If my input value is -4, my output value is -4. And you should immediately recognize this as simply a straight line. What did I do there? 4, 4. Oh, sorry. I've got a point wrong. Can you see right there what it is? This point is wrong. Well, I don't want to do that. Let me go ahead and turn these off. And go back to my points. What I need is 4 and minus 4, which is right here. There we go. Now it's fixed. Delete. So now let's go ahead. The point C is the one I want to delete. So now I've got them right. And we draw my line. You can see we're going to have just a straight line right to the origin that literally goes up at 45 degrees. It literally splits the first coordinate and the third coordinate right in two. So that's the graph of the identity function, is this straight line. So let's pull out some so you can see it. So that's the graph of the identity function. So let's look at some more functions. All of these basic graphs of functions you should know. So the squaring function is given by f of x is equal to x squared. So what would the graph of the squaring function look like? Now, what I want you to do is to try to graph these at first just using a table of values, because pretty soon you're going to have to use a table of values. So in this case, what we want to graph is f of x equal to x squared. So we make a table of values, and here we're going to use, of course we have to use our brain. These are special types of functions. If you realize and you think about it, we'll use that. Still, hold on. My technology is it the technology or is it the user? Well, it's of course the user, right? You always want to blame it on the technology. But I think I'm good to go now. Now I'm still. There we go. So what we want to notice is that for any number a, minus a squared is the same as a squared. So that's a really important property of a function that I will introduce you to later. But this means that for two different inputs, a and minus a, or for example, minus 3 and 3, the output's going to be the same. So when that is the case, I always want to use that knowledge in graphing, because I get a 2 for 1 for my inputs. And it's also true that my output is always going to be greater than or equal to 0. So, as always, we're going to graph x and y values, where y is equal to x squared. And I'm going to start out with using 0, 1, then it's negative, minus 1, minus 2, and 2. And probably we should do even more than that. We'll go 3 and minus 3, and you'll begin to see a pattern, and we'll stop right there. Well, it's not the same color. We can live, right? So let's go. 0 squared is 0 times 0. The output is 0, so there's 1.00. 1 squared is 1. And minus 1 squared is 1. That's what I mean by a twofer. 1 and 1 is another point. Minus 1 and 1 is another point. Minus 2 squared is 4, which is the same as 2 squared. So minus 2 and 4 and 2 and 4. 3 squared is 9, and minus 3 squared is 9. So minus 3, 9, and 3 and 9. So those are several points. Let's go and let's plot them. So I don't know what it's it's doing, why it wants to do more than what I want it to do. Let's just erase those. Why don't I just start off with a whole new canvas. So bringing it up, and we're going to do points. My first point was 0 and 0. My second point was 1 and 1 and minus 1 and 1. My third point was 2 and 4 minus 2 and 4. So we already know that all of my values are going to be positive. My next point was 3. I'm going to have to bring it up just a little bit further or shrink that. So the next point was 3, and 3 squared is 9, minus 3, and 3 squared is 9. So we want to figure out, we want to kind of draw a line through those. And this is what I'm going to do, is I'm going to make the computer do that. And right there the computer has done that. And that is the graph of y is equal to x squared. So it's called an upward facing parabola. The lowest point, called its vertex, is at the origin. Let's do some other graphs. What about the cubing function? It's given by f of x is equal to minus x cubed. So in this case, unfortunately, fortunately or unfortunately, you decide, we have an odd power. So when an exponent is even, so that's 2 to the n for some number n, then we have the following. X raised to that power is the same as minus x raised to that power. So 2 times n is 2 times the number, so this is always even. For example, x squared, x to the 4th, x to the 6th, x to the 8th. But now our function is actually to an odd power. And we don't have that property. As a matter of fact, if x is negative, for example, like minus 2, minus 2 cubed is equal to minus 2 times minus 2 times minus 2, which is equal to minus 8. Why? We have an odd number of negatives. Whereas 2 cubed is equal to positive 8. So I wrote the positive there just to emphasize. So the range values include negative values. But they're really easy to calculate. And again, this function has a special property that I will talk about at another time. It's an odd function, and the property of odd functions will be the focus of a future definition. But just remember right there, the cubing function is an odd function, and the squaring function is an even function. So this is just our table of values. And you should get used to calculating several values because you won't be able to use graphing software on the exams, even if you somehow get away with it taking proctored exams, because Lord knows I can't see what's on your screen. And yes, I could burden you with another software package that makes it so that I could see your screen. I'm not going to do that. You do need to learn how to do this on your own. So again, let's choose values of 1, minus 1, 1, minus 2, 2, minus 3, 3, maybe minus 4, and 4. So 0 cubed is 0. Minus 1, I already know the output's going to be negative, is minus 1 times minus 1 times minus 1. So that's minus 1. 1 cubed is 1 times 1 times 1, that's 1. Minus 2 cubed, we just discovered, was 8, minus 8. 2 cubed is 8. So there's an interesting pairing. Minus 3 cubed is minus 3 times minus 3 is 9 times minus 3 is minus 27. And 3 cubed is plus 27. And 4 minus 4 cubed is 4 times 4 is 16 times 4. My gosh, I don't know. What is minus 4 cubed? It's minus 64. And 4 cubed is 64. So you can think of 4 cubed. 4 cubed is the same as 2 squared, which is 4 cubed, which is the same as 2 to the 6, and that's easier because you go 2, 4, 8, 16, 32, 64. There's 1, 2, 3, 4, 5, 6. Anyway, that's just calculation techniques. So let's go and let's plot some of these values. So my first value was 0, 0. And my second value was 1, 1. And minus 1, minus 1. So whenever it's a negative value, the y value is going to be down here. The next value was 2 and 8, so I'm going to have to scoot out some. 2 and 8. Yeah, the cubing function, it gets bigger really fast. And then minus 2 and minus 8. Then we had 3, which I can't even see here. 3 goes to 27, minus 3 goes to minus 27. So let's just see what that looks like. And there you go. You can see that we were right with the 1, 2, 3, 4, 5 points that we had, but it quickly got much bigger. I mean, literally, we only got to 4, and we were already up here to 64. So that is the cubing function. Our next function is the absolute value function. The absolute value function is always going to be positive. If the input value x is negative, then the output value is the positive value of that. If the input value is 0 or positive, then the output value is the identity. As a matter of fact, what I'm going to do here is I'm going to define the absolute value function using something we just previously discovered. So we're going to let f of x be equal to the identity function. Then we can define g of x is equal to the absolute value of x. So I'm going to define the absolute value of x. Well, the absolute value of x is equal to the identity function if x is greater than or equal to 0. It's equal to minus the identity function if x is less than 0. So, of course, that's not what you were given. You're just given the value of x and minus x. But I wanted to use the fact that we actually now have the identity function f of x equals 2x. So if I wanted to, once I told you that f of x is the identity function, this has to be stated, then I could define the absolute value function, g of x, and denote it that way to be this. If it's confusing, just turn it off. Let's take its graph. What do we know? We know every element in the range is going to be greater than or equal to 0. Let's do a quick table of values so you'll see the pattern, and once you see the pattern you'll be able to go on from there. If you took intermediate algebra and you retained any of it, you already know what this function looks like, and if that's the case you can skip all of this and go on and see what's coming. The rest of you might benefit from some kind of a review. Good enough. Here's my x value. My y is the absolute value of x. So we want to use these observations. 0, 1, minus 1, 2. We're going to be getting 2 first here. Minus 2, 3, minus 3, 4, minus 4. So that's 0, 1, 1, 2, 2, 3, 3, 4, and 4. So let's actually plot that. So my first point was 0, 0. My second point was 1, 1. My third point was minus 1, 1. Let's not even begin to enumerate them. 2, minus 2, 3, minus 3 and 3, 4 and 4, minus 4 and 4, 5 and 5 comma 5, minus comma minus 5, and right there we have it. And I'm not for sure how to do the absolute value function, so we'll just do line segments when we plot it. It's going to look like that. And absolute value functions always look like a V, and this is the most basic one, with again the vertex centered at 0, 0. And then we do the square root function. With the square root function, what you always want to do is, since you can't use a calculator, is you want to use powers of values of x that are perfect squares. So for the square root function, when we do our table of values, our x values we want to choose carefully. Why? Because the square root of any number x squared is equal to x. So if my input number is a number like 0 or 1 or 4 or 9 or 25 or 36, which is 0 squared, which is 1 squared, which is 2 squared, which is 3 squared, etc., then our output value is going to be a whole number. And that's exactly what we want to do, but we have to also do one other thing. For this particular function, this function has a property that none of the others that we've looked at so far has. And since we're looking at the graphs of these functions are real valued functions. Again, what that means is the range, that's the output values, are always real numbers. Real numbers, not complex numbers, or numbers with an imaginary unit. So that means the domain of f of x is equal to the square root of x requires that x be greater than or equal to 0. So the domain is 0 to infinity. And that's the first function that we've had whose domain is not the entire real line. So my numbers x here all have to be in the domain, so I can't get below 0, so no minus 1s or minus 4s. So I'm literally going to use these as my domain values. 0 squared, which is equal to 0. 1 squared, which is equal to 1. 2 squared, which is equal to 4. 3 squared, which is equal to 9. 4 squared, 14. It's not 14. 4 squared, 16. 5 squared, 25. 6 squared, 36. 7 squared, 49, etc., etc. So these are my input values. What I've written here, 0, 1, 4, 9, 16, 25, 36. And my output, 0, 1, 2, 3, 4, 5, 6, and 7. So let's see what that graph looks like. So since my domain is positive, I'm going to move this all the way over here, and we'll go up to 16. So my first one is 0, 0. My second is 1, 1. My third one is 4 and 2. My third point is 4, 2. When I say 4, 2, I mean x is 4, y is 2. My next one is 9, 3. So let me scoot this up some more. All of our outputs are going to be positive numbers too. And my last one is going to be 16, 4. So you can kind of see what that's doing right there. So let's actually take a look. Y is equal to x. And I'm not for sure the square root. I'm just going to do an equivalent. And there you go. And that's what the square root. Notice that it rises ever so slowly. If you're really careful, you could imagine me rotating the xy plane 90 degrees counterclockwise, and you've got a parabola. And that's a very interesting observation, and you're indeed right. That would be the case. So let's go on. So let's determine which of the graphs below is the identity function, the squaring function. That's easy. We've already done those. This is the squaring function. This is the cubing function. This is the absolute value function. This is the square root function, and immediately we know that because it's domain restricted. It starts right there at x equals to 0 and doesn't have anything that are any it doesn't have any range values that are negative and any domain values are negative, and this is the identity function. So this is a piecewise defined function. If you were in intermediate algebra, this is a section we skipped. These are really easy to do, but on the exams, students really miss these functions in their graphing. So pay attention now. So basically, a piecewise defined function is a function whose domain is partitioned into two non-overlapping intervals. That's really important that they're non-overlapping, each one of which has a different defining f of x rule for values in that interval. The reason they can't be overlapping is we can't have two rules applying to the same input value because you don't know what rule to use. So here is an example of two piecewise defined functions, and we're going to go ahead and graph these. It's not difficult at all, and I'll break it down into several points, and then you all can decide how you want to do it. So here's the first one. And the first thing we want to note is our domain is broken into two parts. X values less than 2 and x values greater than 2. Sorry, x values less than or equal to 2 x value is greater than 2. So that if your x value is less than or equal to 2, the rule is you take your input value, you multiply it by minus 2 and add 5. If your x value is greater than 2, you take your input value of x and you add 1 to it. So the first thing I want to do, or the first thing I suggest you do, is you want to draw a line at the split. The split of the domain happens at x equals to 2. So you draw a vertical line at x equals 2. Doesn't have to be anything special, but that's the first step. And what I do is I write on this side the rule f of x is equal to minus 2x plus 5 for elements down here in this portion of the domain, all the way up to and including x equals to 2, which is right here. On this side, I have f of x equal x plus 1. So now we just make two different tables of values. One has f of x equals minus 2x plus 5. And our table of values only needs 2 points. So here the kitty corner zeros can't be used because these are piecewise defined functions. And over here, again, just 2 points is all that's needed. We're going to do f of x is equal to x plus 1. So over here, the domain for f of x minus 2x plus 5 has to be values for x less than or equal to 2. So I'm literally going to choose 2 as one of those values, and the next obvious one is 0. So minus 2 times 2 is minus 4. Minus 4 plus 5 is minus 1. And now when I plug in 0 for x, I get y is equal to 5. So those are 2 points. Let's go ahead and plot them. So 2 and minus 1. Minus 2, that's plus 1, sorry. So minus 4 plus 5 is plus 1. So let's plot the right thing here. 2 and 1 and 0 and 5. And now literally all we do is we draw our line, and that's part of the graph right there. Over here we have to choose values of x, and y is equal to x plus 1 greater than 2. So I can't choose 2 over here, so I'll choose 3 and 5. So that's going to give me 4 and 6. So I'm going to plot the values, 3 and 4, and 5 and 6. But here's the thing. When you draw your line, you have to go all the way and almost touch the dividing line. You can't touch it, and then of course you'll want to extend it on out this way, more or less like that. Now if we were to blow this up, I'm going to go ahead and blow this up. What you could do right here, and probably what my math lab wants you to do, is to indicate that it does not touch that by perhaps putting an open circle there. But that's all there was to it. We literally just graphed the piecewise defined function f of x is equal to minus 2x plus 5 and x plus 4. So let's do another one. So this is a little bit more complicated. One's going to be linear and one's not. One's going to be a parabola opening down, but we can deal with that. So in this case, our domain is divided into two sections, x greater than or equal to 0, so that's literally the y-axis, and then x greater than 2. So I'm going to go ahead and graph a line at x greater than 2. That tells me I can't cross that line. And for x greater than 2, I have y is equal to minus x squared plus 3. On the other hand, for x less than 0, y is equal to 2x plus 3. Now you might say, but it says g of x. But remember, any function, g of x, h of x, p of x, can be replaced by y. So again, we just make two tables of values, and we obey the domain rules. This is going to be a line, so all I need is 2 points. Over here, let's get a few points. Once you kind of see the pattern, you're good to go. So this is going to be x, x, and 2x plus 3. And this is for x less than or equal to 0. Over here I have x minus x squared plus 3 for x greater than 2. So here I have to choose x less than or equal to 0. Since 0 is included into that, I'm going to include 0, and then I'll include minus 2. So 2 times 0 is 0 plus 3 is 3. Minus 2 times 2 is minus 4, plus 3 is minus 1. So right there are my 2 points. Let's go ahead and plot it. 0 and 3 is right there. And then minus 2 and minus 1 right there. So I can go ahead and draw that graph. And right here, since it actually touches the line, what you're supposed to do is make a big blob right there, indicating that that point is included in the graph. Now over here, we have to choose values of x greater than 2. So I can't choose 2, so I'll go ahead and choose 3, 4, and 5. Now they all have to be greater than 2, so I can't use a 3 minus 3, 4 minus 4, none of that stuff. So 3, so minus, the base is x, 3 squared plus 3 is equal to minus 9 plus 3 is equal to minus 6. Minus 4 squared plus 3 is minus 16 plus 3 is minus 13, and minus 5 squared plus 3 is equal to minus 25 plus 3, which is equal to minus 22. So we have the points 3 minus 6, 4 minus 13, and 5 minus 22. I don't think we're going to be able to plot this last one, but we'll try. So 3 and minus 6. So 3 and minus 6 is right down there. 4 and minus 13 is right there. And that's all we have. So all you have to know is that this is going to be a parabola. It's going to be inverted parabola. It's going to be hard to plot given what I have. But we're also going to do something a little bit illegal right here. I'm going to go ahead and assign a value of 2. Even though x has to be greater than 2, I'm going to go ahead and assign a value of 2 for it. So minus 2 squared plus 3 is minus 4 plus 3 is minus 1. So 2 and my x value is 2 right there. I'm going to put a circle right there, and then I'm going to try to draw. And it's really terrible because I'm freehanding, but the point is it's going to be an inverted parabola. As a matter of fact, we can see what that looks like. It doesn't look like anything like I drew because I'm not good at drawing, but let's actually show you what it will look like. So I'm going to draw 2 lines. X is equal to 2, and then the next one is going to be minus x squared plus 5. Nope. There we go. It's minus x squared plus 3. What did I actually do? Oh, so minus x squared plus 3. I just typed it in wrong. There we go. So what you do is you ignore all of cancel that. You ignore all of the graph to the right of our line, and you just put a little circle right there, and you can see what this side of the graph is going to look like. Everything over here disappears, and literally you start right there at the line. X is equal to 2, but you would put an open circle there, and that's what that should properly look like. Okay, so the last thing we're going to do is the greatest integer function. It's also part of what we're learning. So the greatest integer function. So it returns the largest integer less than or equal to x. So it's the greatest integer less than or equal to x. So in other words, to find the value on the number line, move to the left to the next integer on the number line if the number itself is not already an integer. So 5.3 is 5. Why? Because 5 is less than or equal to 5.3. 6.7 is 6. Why? 6 is less than 6.7. Minus 5.3 is minus 6, because minus 6 is less than minus 5.3, and minus 6 is an integer, and minus 6.7 is equal to minus 7. And the plot of that graph I haven't done, but it's going to be basically something like this. It's going to be piecewise defined. So I don't have that here, and what I will do is, it would probably take too long for me to open it up, so I'll just kind of sketch it for you with the restricted domain. So let's bring up here, let's do the restricted domain for the positive integers. So let our domain, so let's define it. We're just going to be kind of graphing this out, okay? This is called a step function. And it is good that you see the graph, and I don't know why I didn't even give a picture of it. So f of x is equal to, and it kind of looks like closed interval. They have that double bar there. So let's let our domain be x greater than or equal to 0. So all we have to do is, I'm going to divide this off a little. We'll just do it I just realized I probably could have pasted over a much better graph for this, but this will be fine. So let's do a table of values. I just want you to see what this looks like for a table of values. We're going to put several values here until we get the hang of it. Well, that'll do, right? So our input value is x, and our output value is the greatest integer function. So 0, what's the greatest integer less than 0? Well, 0. What about 0.5? It's 0. 0.9, it's 0, because this number here, the output value, has to be an integer that's close to, it has to be an integer less than this value, the closest integer. So let's do another one. 2, well, maybe not 2, let's do 1. The output's going to be 1. 1.5, the output's going to be 5. 2, the output's going to be 2. 2.5, the output's going to be 2. So that means, let's get a color here, and let's make this bigger. So I'm going to graph this. This is what it's going to look like. I'm going to make my thing a little bit bigger. So from 0 to 1, it's going to be 0. From 1 to 2, it's going to be 1. From 2 to 3, it's going to be 3. From 4 to 5, 2 to 3 is going to be 3. From 3 to 4, it's going to be 3. And from 4 to 5, it's going to be 4. So it's called a step function. So I'll invite you to figure out what it's going to look like. So clearly it's not continuous, right? If we expanded our domain and we looked at negative numbers, then you can see what that looks like. So that's it for 2.6 graphs of basic functions. We won't do the greatest integer function, but it may very well be on some of your homework. So there's an example. It's really easy. You just have to be careful because you're going, I don't know why they call it the greatest integer less than or equal to x. Well, it makes sense. Let me explain that one bit of oddness too. So let's find the greatest integer. If I will hit the right button, I'll be happy. So the greatest integer, there's 0, and here's 1. I'll label them. I guess I can put a -1 here too. So all of these are integers. Remember, integers are positive or negative whole numbers. So let's suppose my x input value is right here. So the greatest integer less than x. Well, let's look at the integers less than x. Well, 0 is an integer less than x. Minus 1 is an integer less than x. If I extended this one out, minus 2 is an integer less than x. So amongst this list that goes on forever and ever and ever, we take the greatest one. So we take it to be equal to 0. So if x is equal to, say, 0.3, then the greatest integer less than or equal to x is an integer less than x. But of all of our integer choices, which are all of these, we take the greatest of them all. So that's it for this lecture.